projects. In this video, we are going to explain about the project, which is CNN with LSTM driving style classification model based on driver operation time series data. Introduction of the project. The project focuses on advanced driver assistance systems and acknowledges their potential to enhance driving comfort and safety. However, existing imperfections in these systems leading to distrust and limited reliance by drivers. The importance of considering individual driving behaviors in designing vehicle systems for optimal safety performance is emphasized. Recognizing the diverse driving styles among drivers, the project underscores the necessity for vehicles to adapt to individual driving behaviors. It discusses the challenges in current vehicle parameter development and advocates for the creation of the systems capable of accurately identifying driver styles to advanced intelligent vehicle development. Various methodologies employed studying driver styles are viewed, including visual recognition and non-visual signal-based methods. The focus is on signal-based methods due to their effectiveness and minimal invasion of primary privacy compared to visual methods. The project introduces the utilization of deep learning methods, specifically convolutional neural network and long short-term memory networks, for diverse driving style classification. It discusses the integration of the CNNs for feature extraction and LSTM networks for temporal data analysis, highlighting their effectiveness in achieving high classification accuracy. The project outlines its key contributions, including the establishment of a comprehensive driving style dataset incorporating driver operation and vehicle dynamics information. It proposes novel methodologies such as using accelerator and brake pedal signals and integrating LSTM modules with CNNs to enhance classification accuracy and temporal feature analysis. The efficacy of the proposed CNN LSTM model is demonstrated through the experimental results, showcasing its high generalization ability and potential for real world application. Coming to the objective of the project, the goal is to develop systems that can adapt to individual driving behaviors, thereby enhancing safety and comfort by tailoring vehicle responses to diverse driving styles. The goal is to implement the deep learning techniques such as convolutional neural network and long short-term memory networks to accurately classify driving styles based on temporal data streams. The aim is to develop a robust classification system capable of categorizing driving styles into classes such as aggressive, conservative, and normal based on driver behavior data collected from vehicle operations. The objective is to evaluate the effectiveness of classification model using key metrics including accuracy, precision, recall, and reference score to provide a comprehensive comparison of its performance across different driving style categories. The main aim is to strive to create a classification system that demonstrates high generalization ability across diverse driving environments and drivers while also being adaptable to varying data patterns and driving conditions. To implement this project, we need software and hardware requirements. Coming to the hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to the software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. Coming to the first step, which is importing the libraries. In this step, it involves in importing Python packages and libraries that are required for the project. We imported pandas for data manipulation, NumPy for numerical operations, Matplotlib and Seaborn for visualization, scikit-learn for machine learning, TensorFlow for deep learning, and Flask for web development. Coming to exploratory data analysis, in this step, the dataset related to driving styles is loaded and explored to gain insights into its structure, contents, and characteristics. This exploration includes checking for missing values, understanding the distribution of features, and identifying potential patterns or trends. The next step is data processing. Here, the dataset first converted to Pandas data frame, which is a powerful data structure for data manipulation and analysis, and then unnecessary columns that do not contribute to the modeling process or contain redundant information are removed from the data frame to streamline further analysis. Coming to the next step, which is visualization using Seaborn and Matplotlib. Visualization techniques using libraries like Seaborn and Matplotlib are employed to visually explore the relationship between different features in the dataset. This includes plotting histograms, scatter plots, and correlation matrices to understand the distribution and correlations among variables. The next step is label encoding using label encoder. Categorical variables in the dataset are encoded into numerical values using technique called label encoding. This step ensures that categorical data can be used as input for machine learning models. The next step is appending selected features to X and target column to Y. The relevant features are selected and assigned to the input variable X, and while the target variable to Y, which is driving style labels, is assigned to target label Y. This prepares the data for model training. The next step is splitting the data into train and test. The dataset is split into training and testing sets to assess the performance of the machine learning or the deep learning model. Typically, a majority of the data is used for training the model, while a smaller portion is reserved for testing its performance on unseen data. The next step is building the model. In this step, deep learning techniques and architectures are defined and parameters are also defined. The next step is training the model. The model is trained using the training dataset where it learns the patterns and relationship between input features, which is driving behaviors, and target labels, which is driving styles. The training process involves iteratively adjusting model parameters to minimize prediction errors. The next step is Flask framework with SQLite for sign up and sign in. Here, a web application framework like Flask is used to create a user interface for the project. Additionally, SQLite is employed as a lightweight database to manage user authentication such as sign up and sign in functionalities. The next step is user gives input as feature values. Here, user provide input in the form of feature values representing their driving behaviors through the web interface. The next step is the given input is pre-processed for prediction. Here, the input provided by the user is pre-processed to ensure it is in the correct format and compatible with the machine's model's requirements for the prediction. Coming to the next step, which is trained model is used for prediction. The pre-processed input is fed into the trained machine learning model, which then predicts the corresponding driving style based on input features. The last step is final outcome is displayed through frontend. The predicted driving style is displayed to the user through the web interface, providing feedback on their driving behavior. This outcome allows users to gain insights into their driving style and make adjustments as needed for safer and more efficient driving. Now we will know what are the algorithms used for predicting driving style. Coming to the first algorithm, which is CNN. CNN is a convolutional neural network. It is a deep learning algorithm commonly used for image classification and recognition tasks. It consists of multiple layers of convolutional filters followed by pooling layer, allowing the model to automatically learn hierarchical patterns and features from the input data. In this project, CNN is employed for feature extraction from temporal data streams representing driving behavior. By utilizing CNN, the model can automatically learn relevant features and patterns from the input data, aiding in accurate classification for driving styles. Coming to the next model, which is CNN with LSTM. It is a combination of CNN with LSTM networks enhance project's ability to capture temporal dependencies in driving behavior data. While CNNs are adept at extracting spatial features, LSTM networks excel at modeling sequential data and capturing long-term dependencies. By integrating LSTM layers within CNNs, the model can effectively analyze the sequential nature of driving behavior data, considering the temporal aspects such as acceleration patterns, braking behaviors, and steering actions over time. This enables the model to make more accurate predictions of driving styles by incorporating both spatial and temporal information from the input data streams. Overall, the proposed CNN with LSTM architecture provides a comprehensive approach to driving style classification, leveraging the strength of both CNNs and LSTM networks to achieve improved accuracy and performance. As an extension, we applied an ensemble method and the hybrid method to produce a more robust and accurate final prediction. Also, as an extension, we built the front end using Flask framework for user testing with user authentication. We have used accuracy, precision, recall, and FN score, which are the performance metrics to evaluate all the classification models built in the project. So here we have performance comparison graphs for all the models built in the project. This is accuracy score comparison graph where x-axis represents accuracy score for each algorithm and y-axis represents each algorithm name. Similarly, we will have for other graphs also. Coming to the accuracy, it is a proportion of correct predictions in classification task, measuring the overall correctness of the model's predictions. This is the precision comparison graph. Precision is the ratio of true positive predictions to the total positive predictions, representing model's ability to correctly identify relevant instances while minimizing false positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It is the ratio of true positives to the total actual positives, measuring the model's ability to capture all relevant instances without missing any. This is FN score comparison graph. FN score is the harmonic mean of precision and recall, offering a balanced measure that considers both false positives and false negatives, making it suitable for imbalanced datasets. The algorithm which performs well among all these metrics will be used for final prediction. To execute the project, first we have to open the code folder which contains source code files. This is the code folder of the project. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the dataset folder in which we have the data. We use that data for training the models. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is the app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in HTML templates. These are the model files which contain the algorithm information and that will be loaded into the project code during runtime. This is the sign-up file. This file is a database file used to store the user information. And this is the IPYNB file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. Now we have to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we have to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. By this, current directory will change the code folder's path. So here we can observe that current directory is changed to the code folder's path. And here we need to type the command python space app.py to compile app.py file. And now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. Now we have to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, and this web page is built by using the Flask framework. Here we can see a login link. First, we need to click on that. Here we need to provide our credentials to sign in. If you are new users, first we need to create an account. For that, we need to click on create an account and enter all the registration details. I have already registered and I have an account in it, so I'll directly log in. For that, click on I'm already a member. And here I'll provide my credentials, which are the username and the password. Click on login. I have logged in and I'm redirected to prediction page. So here we can see the parameters which are need to be entered. Based on the given parameters, we will get the prediction of the driving style. So the first one is angle. It is the orientation of vehicle related to a reference point measured in degrees. The next one is angle speed. It is the rate of change of vehicle's orientation measured in degrees per unit of time. The next one is ACCZ, which is acceleration experienced by a vehicle along the vertical axis, typically measured in meters per second squared. Coming to brake. Brake is the degree to which the brake system is engaged, often represented as a percentage or binary value. The next one is gyro Y. It is the angular velocity around the vehicle's vertical axis measured in degrees per second. Coming to gyro Z, it is the angular velocity around the vehicle's longitudinal axis measured in degrees per second. The last one is timestamp. The point in the time when the data was recorded, typically in standardized formats such as Unix time or date and time. So now we will enter these parameters. The angle value is 0.352296. 2296. 35 2296. Similarly, we will enter other values also. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. 0.352296. I have entered all of the parameters. Now we will click on predict. So here we got the prediction as driving style is aggressive. Now we will enter other set of parameters. So click on home. I entered all the parameters. Now click on predict. So here we got the prediction as driving style is conservative. Now we will enter other set of parameters. So click on home. I have entered all the parameters. Now click on predict. Based on the given parameters, here we got the prediction as driving style is normal. Now click on log out. In this way, if we enter the driving parameter conclusion of the project, the project successfully developed and implemented deep learning models including convolutional neural network and CNN with long short-term memory to accurately classify driving styles based on temporal data streams. This achievement demonstrates the feasibility of utilizing advanced algorithms for driving behavior analysis. The extension algorithm voting classifier significantly improved classification performance, efficiently combining predictions from multiple base classifiers, and it was rigorously tested in the front-end interface, accurately predicting driving styles based on user-provided feature values. By leveraging these models, the project enables vehicles to adapt to individual driving behaviors, thereby enhancing safety and comfort for drivers and passengers. Tailoring vehicle responses to diverse driving styles, contributing to a more personalized and optimizing driving experience. Through rigorous evaluation using key metrics such as accuracy, precision, recall, and FN score, the project ensured thorough assessment of the classification models' performance across different driving style categories. This comprehensive evaluation provides confidence in the reliability and effectiveness of the developed models. The integration of web framework like Flask with user authentication functionalities using SQLite enhances project's real-world applicability. Users can interact with the system through a user-friendly interface providing input on driving behaviors and receiving real-time feedback on their driving style classification. The project lays a solid foundation for future advancements in the intelligent vehicle systems. Further research and development could explore additional features, refine algorithms, and optimize model performance for broader adoption in automotive industry applications. Continued innovation in this domain promises to further enhance vehicle safety, efficiency, and overall driving experience.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.